Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we will continue our discussion in this module starting with the critically damped case when the damping frequency, the driving frequency matches with the natural frequency of the system. Okay, so what we have is the following. X double dot plus 3x dot plus 2x is 10 cos t. Okay. So then what we have is we look at one particular example. We try and solve the system. We quickly see that we assume x having this form of solution c times e to the power it. Well, why it? Because this the complex analog of the right hand side is 10 e to the power it. And then when we solve, we find that c comes out to be 10 1 plus 3i, and from here we can find our so this is 10 times 1 minus 3i. From here we can find the particular solution. My particular solution is 10 times 1 minus 3i times e to the power it, and then to find the particular solution we take the real part of this solution, which is going to give us cos of t plus cos of 3t, plus 3 times sine of t, and then we add it to the homogeneous system, the homogeneous solution, which is going to be the homogeneous system xh is a times e to the power minus t plus b times e to the power minus 2t. That is by solving this system, x double dot plus 3x dot plus 2x equal to 0. That is a homogeneous system. Okay, and that is how we solve these typical problems. So then let us come back to a discussion of the case when the damping or the natural frequency is equal to the driving frequency, or the so called resonance of the oscillatory mode. Okay, so resonance is a very special scenario. Resonance of an oscillatory mode. Okay, so what we have is typically resonance is not good in real life examples. Some of the real life examples are the so called the London Bridge disaster in 1950s, where the soldiers who were marching on the bridge had a frequency which was the natural frequency, which matched with the frequency of the swinging of the bridge. And then we will see, as we will see in this analysis, that led to a catastrophic increase in the amplitude of the oscillations, leading to the final collapse of the bridge. Right? So typically resonance is not good in real life. It leads to a catastrophic increase in the amplitude of the disturbance. Okay, so let me just show you. So to begin with, we saw that, so recall, if we start with our again our complex solution to the driven damped case, we find that the amplitude of the complex solution was f naught divided by square root omega square minus p square whole square plus 2kp whole square, right? And then what we have is that a is well, let me call this quantity inside the square root as f of q, which is omega square minus q whole square plus 4k square q. Okay. Okay, so then what we have is, so what do we get? From here we see that f prime, let me do a bit more analysis in this expression. So f prime q, so where my q is p square. Okay, so f prime q comes out to be 2 times q minus omega square minus 2k square. Okay, and from here we see that this quantity fq is going to decrease if q is less than omega square minus 2k square, right? And it increases otherwise. Okay, so what have we got here? So let us look at two particular cases in this analysis. Case 1, let us assume that omega square is greater than 2k square, that is, this quantity is greater than 0, and in this case we see that q so fq must be, this quantity fq must be positive. Why positive? Because otherwise the square root is not defined. And in this case we have that q is greater than omega square minus 2k square, and since we have assumed that this quantity is positive, we get that q is positive, right? So which means that q is positive, and positive means that fq is going to start to for this particular scenario we will see that the amplitude will start to decrease because q is starting to increase, and it is going to decrease and it will show some well, the amplitude is starting to first increase and then decrease before eventually showing a maxima in between. So what have we got here? So in this particular scenario a is such that a is f naught by so in this particular case we have f naught divided by 2k times omega square minus k square. This is the maximum amplitude that we get. How did we find this? We find we take f prime q, set it equal to 0, find what is q. So q is omega square minus 2k square, plug it back into our expression here in this quantity, and from here we find that this is what we get. Okay, so then what do we have? The second case is when omega square is less than equal to 2k square. If that is the case, then we have that in this case we have that q minus omega square minus 2k square, this quantity is less than equal to 0. So we have and q is equal to p square. So this quantity is always positive, and so there this is always going to be positive and it's always increasing with p. So which means that the amplitude a always decreases with q and it goes to 0 as q increases, right? So there is no maxima in this case. If we plot the amplitude a versus q, there is no maxima in this second case, and in this first case if we plot the amplitude versus q, we get the following. We have a maxima before which the amplitude starts to decay. Okay, so these are my two scenarios. This particular first case is the case of resonance, where we see a massive increase in the amplitude of the oscillation before it starts to decrease, and that is what I was saying. If your oscillation of the system is at this particular amplitude, which is a max or q max, then we are in trouble. That is, the system is going to show massive oscillations. Okay, so then let me now talk about general driving forces. General driving forces. It turns out even in the case of general driving forces, f of t, we can write those driving forces in terms of its Fourier modes. So what I am saying is the following. The general case of periodic driving. The general case of periodic driving. So which means my f of t, that was my right hand side of my damped oscillator equation. F of t in general, the general case we can always write this f of t in terms of its Fourier modes, which means that I can write this to be equal to a naught by 2, the Fourier expansion, plus summation n from 1 to infinity an cos of nt plus bn sine of nt, right? And we see that this is also equal to an 1 over pi times integral minus pi to pi, and this is f of t cos of nt. So these are my formulas for the Fourier modes. Bn is 1 over pi minus pi to pi f of t sine nt dt. Okay, and so that by plugging all these Fourier modes, we can express my general driving force in terms of these Fourier modes. So let us look at an example. So the example says find the driven response. Find the driven response. So what does the problem says? It asks us to find the particular solution of the simple harmonic motion. So find the driven response of the damped oscillator which is given by x double dot plus 2kx dot plus omega square x is equal to f of t. Okay, and where f of t is given by f naught, where t is from 0 to pi, and this is minus f naught where t is from pi to 2 pi, right? And we find that f of t will exhibit this particular expression is going to exhibit a so-called step function, right? So from 0 to pi we have the positive values, and from pi to 2 pi we have a negative values, and then it is periodic step function. So and periodic thereafter. Okay, so we have to find the driven response or the particular solution for this sort of a driving force. The way to do this problem is to express this f of t in terms of its Fourier coefficient, as I just said, right? So if we start to calculate what are my Fourier coefficients for f of t, my an comes out to be 1 over pi times minus pi to pi and f of t cos of nt dt. Now f of t, we can always break this integral from minus pi to 0 and from 0 to pi. Why? Because in these two intervals my function f of t is a constant, either it is f naught or minus f naught. So now those constants can be taken out, and we are essentially integrating with respect to cos, right? So cos gives a sine, and sine at minus pi and sine at 0 will be 0, and again here and at these two limits will be 0, and eventually we will get that ans are 0, right? So this is when n is greater than 0, and when n is equal to 0, then cos of nt will be 1, but that integral also vanishes because we have equal and opposite integrals, minus f naught here and f naught here. That also cancels out. So anyway, my ans are zeros whether n is 0 or n is greater than 0. So an is out. Now let us calculate what is bn. My bn is 1 over pi times integral minus pi to pi f of t sine of nt dt, right? And this is equal to minus pi to 0 plus 0 to pi, and we integrate, we see that this is 2 over pi integral 0 to pi f naught sine of nt dt. Okay, so what have we got here is we see that the two integrals are equal and opposite, so hence we have reduced the integral into a single integral and put a factor 2. This f naught is a constant, and after integrating we quickly get the answer that this is 2 f naught by pi times 1 minus 1 to the power n over n, which means that if n is even, we see the bn's are 0. If n is odd, then bn's will add up and give you 2. Okay. So now my f of t can be written using the Fourier expansion as summation n from 0 to infinity. Well, the 0 one will not play in part, so it has to be n from 1 to infinity times 2 f naught by pi 1 minus 1 to the power n by n times sine nt. So essentially we have represented our driving force in terms of its Fourier as mode sine and cos, and this is my bn. Okay, and then finally we can find my particular solution. This is c times e to the power I, well, I t, well, I and t, where n is the frequency of the oscillation, n is the frequency of f of t. So and c comes out to be c, the amplitude cn comes out to be bn divided by I'm just using the formula for the amplitude we described few slides back, times divided by omega square minus n square plus 2 ikn plus 2 ikn, and then we see that this is also equal to, we take a we rationalize this system and we find that this is also equal to, we can rationalize, and then of course my solution x, particular solution will be this quantity cn times e to the power I and t, where cn depends on bn, right? So we plug all these quantities here and we take a real part, well, not the real part, we take an imaginary part of this quantity to find my solution. Why? Because why imaginary? Because we have signs sitting in the Fourier expansion of f of t. So we need to take the imaginary of x of p to find the real solution. Okay. So then that discussion closes our chapter on how to find the damped driven and undamped driven simple harmonic oscillators. So now in my next setup I am going to talk about some practical applications of damped and driven harmonic oscillators. One such example is the so-called seismograph. So what is seismograph? Seismograph is an equipment which measures the earthquakes, right? So we can typically model earthquakes as oscillations of the earth's surface, right? And due to this oscillation, the seismograph also oscillates. Typically the seismograph is in a very simple setup. It is like a mass which is being held up by a spring, and the spring is allowed to oscillate back and forth, right? So if you have an earthquake or some tremors or oscillations, this mass spring system is going to oscillate, and that is going to, and the period of oscillation is going to tell us some details about the period of the eventual tremors, right? So seismograph is a device which measures earthquakes. Okay, and we want to find out how this equipment works, right? So typically we have the horizontal, we have both, in fact in a real setup we have both the horizontal and the vertical movements of the seismograph. Let me denote it by SG, right? But the problem at this point is that we are going to look at only the vertical movement of the seismograph. So we restrict only to vertical movements. We restrict only to vertical movements. Okay. So then what we have is, suppose we have we continue. Suppose we have we have the ground as our fixed frame, right? So we have a fixed frame. We need to fix our frame of reference with which we want to study this oscillation. So our ground is our fixed frame. Okay. Of course, when the ground shakes, then the oscillations are going to be with respect to that ground. Okay. So I should rather say not fixed frame, but the ground is our reference frame, right? So the reference frame can also move, right? Okay. So then let us say my x of t is my downward displacement at time t. Okay. And let us say my small x of t is the extension of the spring with respect to its equilibrium. Okay. So the downward the extension x of t is the extension of the spring with respect to its equilibrium. And so the total displacement, from here we find that the total displacement comes out to be x plus capital X. The total displacement is x plus capital X with respect to an inertial frame. Okay. Okay. So then in this case, my equation of motion, I can quickly write the equation of motion in the vertical movement scenario, that we have that m times the double derivative with respect to time of x plus capital X, right? So that is the total displacement is the equilibrium plus the extension of the spring. So this is the extension, this capital X is the equilibrium. And so this is also equal to minus 2 times mk dx dt. So what we are trying to, we are looking at a more general scenario where the spring is damped. Minus m times omega square x. And simplifying this setup, we see that this is equal to x double dot plus 2k x dot plus omega square x is equal to minus capital X double dot. So we have reached back to our original system where we are studying the damped driven oscillator, and on the right hand side we have some function which can again be expressed in the form of the Fourier series, right? So let us take this expression on the right hand side to be a Fourier function. Let us say that this is a times cos of pt, a Fourier function, and then again we go back, we plug this capital X here. So this capital X double dot with a minus sign comes out to be ap square cos of pt. And again, once we find our particular solution, we see that the amplitude of the particular solution comes out to be capital A times, where A is this amplitude of the driven force, A divided by 1 minus A divided by A divided by absolute value of minus 1 plus 2I k by p plus omega by p whole square. Okay. Okay. So that is a simple case where we have looked at this driven scenario of the seismograph, and we have found the particular solution of the oscillation. So now what we have is, let us look at the case where we have the coupled expression for multiple multiple objects. Okay. So we are looking at oscillations which are coupled, so slightly complex scenario. So coupled oscillations and normal modes. Coupled oscillations and normal modes. we see that we have two masses which are being attached to some support, two masses. The supports are fixed. The masses are attached to each other with a spring and also to the support with a spring. So now notice that in this set of two masses, if one mass gets extended, let's say by a distance x, and the other mass gets extended by a distance y, then the net, there won't be any net change in the length of the spring. There will be a compression somewhere by a distance minus y plus x, and so on. So which means that if there is a tension in the spring due to extension, there will be a compression in the spring due to the compression itself. So there is no net length change of the spring because the supports are rigid. Okay. So then in this case we can assume linear restoring force. We can assume linear restoring force and zero damping. Linear restoring force and zero damping. And let us say we have x and y be the displacement of the bodies. X and y be the displacement of the two bodies from their equilibrium position. From their equilibrium position. Okay, at time t. Okay, so let us now try to set up. So at any given time, at any time t, we will have the net extensions of the spring, as x. So if this is x, and let's say this was let me take the notation properly, right? So if we have this length to be y, whatever y is, compression or extension, then this length will be y minus x. Okay. So the net extension is x, y minus x, and let's say this was extension, this would have been, y would have been compression, so this is minus y. So the net extensions are as follows. Now suppose at the spring constants, assume the spring constants are, alpha, 2 alpha and 3 alpha, okay, or 4 alpha. So which means the first spring has a constant alpha, the second spring has a constant 2 alpha, and the third spring has a constant 4 alpha. There are 3 springs. So then we can quickly write the equation of motion. The equation of motion reads as follows. We see that m times x double dot is equal to minus alpha of x. So one spring gets extended, so that is going to push with a restoring force, hence the minus sign, plus 2 times alpha y minus x. The other one gets compressed, so we have a restoring force with a plus sign. And then the second one is m times y double dot is minus 2 alpha y minus x. The sign is opposite for y, and minus 4 alpha times y. And then all we have to do is to solve these two set of equations. We can always assume, we can always simplify this setup by assuming n square to be alpha over m, and from here we see that x double dot is plus 3 times n square x minus 2n square y is 0, and y double dot minus 2n square x plus 6n square y is 0. Okay, and then when we solve these system of two equations, we find that x is a times cos omega t minus gamma, and y is b times cos omega t minus gamma. We'll have to find what are these values omega and gamma, right? Now notice that if we again assume some solutions, right? If we assume solutions x and y of this form, plug it into our system of equations, we are going to, and we have to find a non-trivial solution. Notice the trivial solutions are x equal to 0, y equal to 0. So x equal to 0, y equal to 0 is a solution of the system. We don't want that. We want a non-trivial solution. So when we plug it, we see that we get the following set of equations: 3n square minus omega square times a minus 2n square b minus 2, well, this is equal to 0, and minus 2n square a plus 6n square minus omega square b is equal to 0. Right? Notice that I can write this system of two equations using our matrix vector formulation, and we don't want a or b to be equal to 0. We don't want that. Right? So then, which means that we have to keep the determinant of this system. To do that, we have look at the matrix here. So 3n square minus omega square minus 2n square minus 2n square and 6n square minus omega square. So this matrix, its determinant has to be set equal to 0 so that we get a non-trivial solution. Right? And from here I can find that my omega comes out to be either 2n square, or it comes out to be well, omega square comes out to be 2n square, or it is 7n square. Right? And these are my two roots of the system. And once we have omega, we plug it back into our form of solution that we had assumed. X is a cos omega t minus gamma, and so on. So for example, if we look at the slow mode, that is when omega is omega square is 2n, or omega 1 is square root 2n, right? In this case, if we see, we find that let me call this matrix vector system as system A. We find that from 1, well, from 1. So from 1 we find that A is equal to B, and we find that my solution is as follows. We have X is, well, what have we got? Well, A is 2B, sorry. So X comes out to be 2 times gamma, well, 2 times delta cos of square root 2n minus gamma, and Y comes out to be delta times cos of square root 2n minus 2nt minus gamma. Okay. So then what have we got is, so this is my solution finally. For the fast mode, we see that omega 2 square is 7n, and we find that omega 2 comes out to be well, omega 2 square is 7n, and we find the solutions as x is equal to delta cos of square root 7nt minus gamma, and y is equal to a, well, it comes out to be a is equal to minus b is equal to minus 2a in this case, and so this is minus 2 delta cos of square root 7nt minus gamma. Okay. And then from here we can write the most general solution: x is this plus this, and y is this plus this. Okay. So x is, let me call this as delta 1, this is a delta 2, and then when we add these two, we find our final expression for both x and y. Okay, so one last question I want to highlight is this combined motion periodic? So is the combined motion periodic? Motion periodic? Well, it turns out no. Why? Because notice that the first root comes out to be square root 2, so omega 1 is square root 2, and omega 2, the fast mode, is square root 7. So we need to see the ratio of the two frequencies. If the ratio of the two frequencies is a rational number, then we can say that the combined motion is periodic. Then it is periodic. Of course, in this case, omega 1 by omega 2 comes out to be square root 2 over 7, which is not rational, and hence the motion is not periodic. Well, where does this expression comes from? Readers are requested to see my previous course on nonlinear dynamics, where we had shown that the rational ratios of the frequencies lead to periodic combined motion, even though we have individual frequencies which may be irrational. As long as the ratio is rational, then the combined motion is periodic. So thank you so far for listening, and let us continue in the next module.